Well, welcome to everybody. This will be the second lecture in the LIU Nursing Math program. My name is Susan Tennant. The lectures in basic algebra are occurring every 2 weeks at this time, so you'll see me for 2 hours today, and then again on October 29th for 2 hours, also from noon to 2 p.m. I want to remind everybody that the help sessions for questions that you may have or remediation in certain areas occur on Thursdays from 4:30 to 5:30, and on Fridays from 10 to 11. Okay, today we'll be looking at some of the basics of algebra, and we're going to start with variables and algebraic expressions. Now, what is a variable? Well, a variable is a letter or a symbol that we use to represent a number, or we can use it to represent a set of numbers. For example, if you look at 3x plus 4, in this expression, you can see 3 and 4 are numbers. X is called the variable. Now, why is it called a variable? Well, it's called a variable because it can vary. The idea is that we want to be able to express relationships that involve operations of arithmetic, but also that could allow us to have different values for numbers that we plug into these expressions. So let us take a look, for example, at various algebraic expressions that contain variables and numbers and which are going to be combined using arithmetic operations. So for instance, if we have the operation of addition, you can see an algebraic expression that would involve addition uses the symbol plus, 2a plus 16. In this expression, the 2 and the 16 are clearly the numbers, and a is the variable. In subtraction, for instance, we would have a minus 6. A is again the variable. 6 is the number, and we show that the subtraction occurs by use of the negative sign or the subtraction sign. Multiplication, if we want to indicate 2 times some number, we could represent the number, say, by b, and so we would represent this as 2b. 2 with the b written right next to it, and without any symbol between it means multiplication. And division, for example, we have the expression x minus 5 divided by 2y. It tells us that for some particular choice of a number for x and some particular choice of a number for y, we subtract 5 from the value of x, we multiply y by 2, and then we divide the numerator by the denominator to perform the division. Now let's see some examples of how this works. For example, suppose John is x years old today. How old was John b years ago? How old will John be c years from now? Well, b years ago tells us that we subtract b from John's present age, which we've designated as x. C years from now tells us that we add c to the number of years that John is now. Now, if you find it confusing at first to be dealing with variables, you can always substitute a number just to see how it works. So for example, if you're not sure how to do how old was John b years ago, you can pick a value for John's age and then subtract the value that you choose for b and see how that works. In other words, even take your own age and say, how old was I a certain number of years ago that you could select. B years ago, you can select the number and see how old that would be. And then you realize that you have to subtract b from the present age to determine how old you were, say, b years ago. And then you can do the same thing c years from now, except now, of course, you're adding. And you can always pick a number just to see it as an exact example and realize that c is used here to indicate that we could use any number, and the process of finding the answer would be the same. Let's take a look at some examples of variables and algebraic expressions. Supposing we wish to express in cents the value of x dollars, y dimes, and z cents. And again, if you are confused by the use of variables here, you can start out by picking exact numbers, seeing how they work, and then trying to generalize it to x dollars, y dimes, and z cents. Now, we know that there are 100 cents in each dollar, and we know there are 10 cents in each dime. So if you want to find the value of these, of the different kinds of money here, the different kinds of coinage, you can multiply the x dollars by 100, which is the number of cents in each dollar. You can multiply the Y dimes by 10, which is the number of cents in Y dimes, and then add the Z cents. This puts everything in terms of cents. So we have 100X for the value of the dollars, 10Y for the value of the dimes, and Z for the value of the cents. Then you add them all up. One of the things you really have to keep in mind here is that there's a difference between the number of these coins and the value of these coins. For example, if you have $1 in your pocket, that number is 1. You have one actual piece of paper. But what is the value of that dollar in cents? The value is 100 cents. So always try to keep in mind the difference between the number of items that you have and what their actual monetary value is. Now, and remember that if you're not sure, because the variables kind of throw you off, you can always substitute numbers to check to see if the answers that you got made sense, and then go from that to generalize to the particular problem that you're looking at. Okay, let's look at another question. The floor of a rectangular room measures A feet by B feet. How many square yards are needed to cover the floor? So let's take a look. Okay, say this is, I mean, you have to imagine this is a better rectangle, that the floor measures, say, A feet by B feet. And we want to know how many square yards of carpet are needed to cover the floor. Well, if we multiply the A by the B, we're going to get square feet, and then we have to convert to yards, to square yards. So let's take a look at how that works out. Okay, we have that the area of the floor will be the length times the width. We multiplied the A by the B, and that would give us square feet. So we have to divide each by 3 to turn it into yards. Then if we multiply A over 3 yards by B over 3 yards, we would get AB over 9 square yards of the carpet that are needed. Now, actually, I would prefer, generally, if you're going to do an area problem, use A for area, and then perhaps instead of saying A feet by B feet, use X and Y, so that you're not inclined to confuse the A for area with the A that you're using as a variable. I just think it works out better, but clearly it doesn't matter a whole lot. Or you can use L and W. That's very common too. You'll come upon L and W being used as length and width. And so then you would just, this is more suggestive of what the answer is. So then you would just wind up with that the area comes out to be your length that was given in feet here, divided by 3 to turn it into yards, times the width, again divided by 3 to turn it into yards. And then the final answer is going to be L times W over 9 in square yards of carpet needed. And remember, again, you can always substitute numbers to see if the answer that you're getting makes some sense. The next thing we're going to look at is ways in which we simplify algebraic expressions. If we rewrite an expression in a simpler form, we call this simplification. If we want to simplify expressions, we have to consider what operations are involved and look for like terms. Like terms are terms that have the same variables and the same corresponding exponents. Only like terms can be combined by addition and subtraction. Right? This is not an issue when you're multiplying, but for addition and subtraction, you can only combine like terms. So if we look at the first algebraic expression over here, and we search for the like terms, we see that the 2x squared y and the minus x squared y are the same because they both involve a coefficient that is a number in front of the variables. In this case, 2. In this case, it's like a -1, understood. X squared and x squared, y and y. So these terms are like terms. They can be combined. If you combine 2x squared y and minus x squared y, then you're just going to have 1x squared y, or just, we don't usually put the coefficient of 1 in front, so just x squared y. Also, if we look at 2pq plus 2p plus q squared plus 4p, the only ones that are the same are the 2p and the 5p. So those are the like terms, and they can be combined to give 7p. And then, if you look at the final algebraic expression, 3a plus 4b minus 15b, here only the expressions in b are like terms. The plus 4b and the minus 15b would combine to give us a negative 11b. So let's look at the next problem where we have to simplify this expression. Before we can perform the simplification, we really need to distribute the multipliers p in this case and 2 in this case so that every term is without parentheses. So first, distributing the p, in this case, we have 3p squared, and here we have 2p squared, and it looks as if we have an error here. Yes, it looks as if this was miscopied somehow. All right, so if we want to keep it as 2p plus 4, we would have to change this to a 2. Okay, and then this becomes 2p squared instead of 6p squared. So this gives us 2p squared plus 2p squared gives the 4p squared over here. 2p squared plus another 2p squared would make a total of 2p squared plus 2p squared, and so the final total is going to be 4p squared. And then the p has to distribute over the 4, that gives us the 4p. The 2 distributes over the p squared, as we said already, and the 2 multiplies the 5, giving us 10. So we wind up now with 4p squared plus 4p plus 10 after adding the like terms to get our final answer. To take a further look at this idea, let's identify 3 groups of like terms in the following list. We have something here involving an x squared y. So we look to see if there's anything else involving x squared y. Well, if we look at this, we look at this, both of these terms involve x squared y. Therefore, they are like terms. Okay. Here we have a 4 without any variables. And here we have a minus a half without any variables. So the 4 would connect with the minus a half. And now here we have an xy squared and another term in xy squared. So this term would be like this term. And the x squared y squared term has no match, so that stands alone. So if we wanted to combine these things, we would be combining only the like terms. And here we have the like terms as specified in the previous screen, the 3x squared y and the 0.6x squared y as like terms. Also 4 and the minus a half, and also minus 2 xy squared and the 2/5 xy squared. Now remember that you can perform addition and subtraction only on like terms. Let's look at the next question. We want to simplify this expression. Now this expression involves only additions and subtractions. Therefore, we can only combine like terms. So we have to identify what the like terms are. Here you have a term in y and another term in y, so those would be like. Here you have a term in x, another term in x, so those would be like terms. And then the remaining terms, the ones in z. So let's take a look at how these combine. We see that the 3y combines with its mate, in effect, the 5y. The 2 like terms combine to give 8y. The 2x, the minus 2x add to 0. In the final answer, we don't have to include the 0, but we're putting it in here to make a point that these are additive inverses, and so they add to 0. And here, the negative z and the plus 3z add to give 2z. So our final answer is just the 8y and the 2z, and the terms in x dropped out because they added to 0. Now let's look at another example involving simplifying algebraic expressions. We cannot perform the additions in this problem or the subtractions as long as we have the multiplication. Remember, in order of operations, multiplications have to come before additions and subtractions. So we have to do these multiplications to simplify the expressions, and then we can look for like terms that we can add. So first, distributing the 5 over the a plus b, we have 5a plus 5b. Distributing the negative 4 over the a minus 3, we have minus 4a and plus 12. Remember, the negative 4 times the negative 3 is going to give us a positive result. And then distributing the 2 over the next expression, we have plus 8b plus 4. Okay, so now we can look for like terms. Now that we've gotten rid of all the multiplications, and we see we have terms in a, the 5a and the minus 4a. We have terms in b, the 5b and the plus 8b. And then we have the constant terms here. So moving along, we see that the 5a and the negative 4a combine to give 1a, and we don't have to write in the 1, the coefficient of 1. If we just write a, we understood that the coefficient is 1. We understand that. The 5b and the 8b add to give 13b, and the 12 and the 4 add to give 16. So our final result, after distributing and combining all like terms, is a plus 13b plus 16. We wish to find out how to deal with something called equations. An equation is a statement of equality between two expressions. Equation contains the notion of equal. So if we have a statement, the sum of a number a and 14 is equal to 18, it means we're dealing with an equation and it uses an equal sign. So the number a is denoted here by the symbol a. Adding the number 14 means addition, and it equals equal sign 18. So that's the equation we get from going from the statement of words into the mathematical symbols. Twice y decreased by 8 is equal to 2. If y is the variable, we have twice y decreased by 8 means we're subtracting 8, and that's equal to 2. The difference of a number b and 12 is equal to 4. Difference means subtraction. So the number b, taking away 12 or less 12, gives us 4. So this shows us equations involving addition, equations involving subtraction. Whenever you see sum, you know you mean addition. Whenever you see difference or decreased, we know we mean subtraction. A formula is an equation that relates two or more quantities. So, for instance, we say the perimeter of a square is 4 times its side. We can express this as a formula if we use P as the perimeter and S as the side. This formula shows us that the perimeter is 4 times the side. Or the area A of a rectangle is equal to the product of the length and the width. So the area A is equal to L times W. So now let's take a look at some problems involving these ideas. Supposing we have the issue 3 times a certain number equals the number increased by 20. What equation could be used to find this number? Well, we have to have something that we're going to use to stand for the number. So supposing an obvious choice is n. All right, let's suppose we let n represent the number. We're saying here 3 times the number, so that means 3 times n, is equal to, so when we say is equal to, that means an equal sign, the number itself increased by 20. Remember, increase means we add. So this is the equation or formula that relates the English sentence to a sentence which is a symbolic sentence and which can then be solved by algebraic processes. N is the number, 3 times the number equals a number with 20 added to it or increased by 20. Let's consider another question, a little more complicated. James has 4 times as many peanuts as Sarah. Together they have 35 peanuts. What equation could be used to find the number of peanuts each person has? Well, you want to set up something to stand for the number that James has and the number that Sarah has. So we need to have a variable for starters. So supposing we use an obvious variable of P for peanuts. And since James has 4 times as many as Sarah, the logical choice is probably to let P equal the number of peanuts that Sarah has. And then James is 4 times that, so 4 times P is the number of peanuts that James has. So if we know that together they have 35, together means if we add them up. So if we add P to 4P, we should get the total number of peanuts, or 35. And sure enough, we let P be the number of peanuts Sarah has, 4P represent the number of peanuts James has, then adding them, P to 4P gives us the total 35. And of course, if you wish to proceed and actually get an answer for this problem, you then can combine your like terms to get 5P equals 35. P then is equal to 7. And then 4P equals 28. So 7 represents the number Sarah has. Oops. And 4P represents the number that James has. I seem to keep hitting the wrong key accidentally. Sorry about that. And so if we add up Sarah's to James, we get the total 35. Okay, let's look at another problem. A tank holds 1,500 gallons of water, has 3 pipes that drain it. The first pipe is letting out 8 gallons a minute. The second pipe, 10 gallons, again, per minute, we should say. And the third pipe, 12 gallons per minute. We want to write an equation that could be used to find out the total number of minutes it will take to drain the tank. Okay, so supposing we let M, and it doesn't matter what you use, but sometimes we try to pick variables that are kind of suggestive of what we're finding. Here we're trying to find minutes. So, okay, let's use M to stand for the number of minutes to drain the tank. So the first pipe would drain 8 M gallons in the time that we have for the total. The second pipe will drain 10 M gallons. We seem to have somehow lost our variable. And the third pipe will drain 12 M gallons. If we add all of these up, the number drained by the first pipe to the number drained by the second pipe to the number drained by the third pipe, we find that the total makes 1,500. Now, this can also be represented this way, but frankly, I think that most people are going to find this the most reasonable way to represent the equation. Okay, I mean, the second one is trying to express the idea that if you take the total number of gallons and then you take away the amount from that the first pipe contributes to the removal of gallons of water, and then the next pipe, what it removes, and then what the next pipe removes, you wind up with 0. But I don't think most people tend to think about it that way. So perhaps the easiest way to think about it is that the amount contributed by one pipe to the second to the third gives you the total that was in the tank. So I think this is probably a more straightforward way of thinking about it, although this other way is also acceptable. Okay. Now, we want to use equations that involve addition and subtraction. Therefore, we need to review some of the properties of addition and subtraction. You're probably familiar with these already, but we're just going to go over them to remind you. So we have first the addition property of equality. If you have an equation, A is equal to B, and you want to add a number C to both sides, you still have an equality. So A plus C will be the same as B plus C, and because you've added equal things to both sides, it's called addition property of equality. Subtraction works the same way. If you have real numbers A, B, and C, if A is equal to B and you subtract C from both, A minus C is going to be equal to B minus C. Now, supposing we want to solve the equation x plus 2 is equal to 12. If we want to isolate x, what do we need to do? Well, we need to get it all by itself. How do we get it all by itself? If we have a plus 2 here, to undo that, we're going to want to subtract. So we're going to subtract 2 from both sides of the equation using subtraction property of equality here. And that will give us x. The plus 2 and the minus 2 will add to 0. And the 12 minus 2 will give us 10. Okay. So here, using subtraction property of equality, we see x plus 2 minus the 2 is equal to 12 minus 2, and x is 10. Now, if you want to check a solution, you always have to go back to the original equation, always. Because if you go back to some intermediate process, if you made an error going from the original to the intermediate step, you may find out that everything looks okay, but you jumped over the part where you made the mistake. So the key in checking is always to go back to the original equation. The original equation here is the x plus 2 equals 12. So here we had x plus 2 equals 12, the original. We had a value of x equals 10. We substitute that for x. 10 plus 2 equals 12. Is that true? Yes, it is. And so we have 12 equals 12, and that proves that the equation is solved correctly. Okay, let's take a look at another equation. How are we going to solve this? 3x minus 3 equals 2x minus 8. Okay, well, we can subtract 2x from both sides. This will add to 0. And now we have x, 1x, or just x, minus 3 equals minus 8. You can now add 3 to both sides. And we will get x equals minus 5. Guess it didn't give us solutions here. Okay. Now, students will very often ask me, do we have to check? Well, you know, it seems obvious to me that you don't have to check, but if you have a way of checking an answer, wouldn't that be an ideal thing to do? I mean, after all, if there's a way of determining if your answer is right or wrong, I would think you'd want to know it. So while you might not be specifically instructed, check your answer, probably you will want to check your answer to make sure that it is correct. All right, let's look at another equation. Solve for m. In this case, remember, we have to get rid of this multiplication first. So multiplication of m minus 3 by 2 requires that we use a distributive property. The 2 has to distribute over the m, and the 2 has to distribute over the negative 3. So this gives us 2m minus 6 equals 3m. Now you can subtract 3m from both sides. This will add to 0. And we have minus m minus 6 equals 0. If you add 6 to both sides, you get minus m equals 6. And therefore m is negative 6. You can multiply both sides of this equation by negative 1. Next question. The sum of a number and 15 is negative 4. Find the number. Okay, I don't know how I wound up with a stray number there, would get rid of that. Okay, so the sum of a number and 15 is -4. Sum means addition. If we let the number be, say, n, okay, we have the number n added, because sum means addition, to 15, and this gives us -4. The is means equals. So we now subtract 15 from both sides. These add to 0. This adds to -19. And so n is equal to -19. If we go, yeah, sorry about that. Okay. Oh, and this time they gave us an answer key. All right, so the sum of the number and 15 is -4. N is the number plus 15 is -4. We subtract 15 from both sides, n is -19. Now we would like to look at solving equations, but this time using properties of multiplication and division. Okay. The multiplication property of equality says that if we have two numbers that are equal, like a and b, and then we multiply by the same number, c, then a times c is going to be the same as b times c. The same thing holds for division. Of course, you have to be very careful in division that c is not 0. Remember, we always make the stipulation that we cannot divide by 0. Okay. So if a is equal to b, then a divided by c is equal to b divided by c, provided c is not equal to 0. So supposing we want to solve the equation 2x equals 24. Well, using the division property of equality, divide both sides by 2, we get x equals 12. We check by going back into the original equation, substitute 12 for x, and we see that the answers check. So let's look at this problem, solving equations using multiplication and division. We have an equation here we wish to solve for k. The coefficient is -2/7. If we multiply both sides by the multiplicative inverse, sometimes known as the reciprocal, we would get the following. We have -2/7k is equal to 10. We multiply by the multiplicative inverse, -7/2. Okay, this is also, you've heard this term, the reciprocal. And if you multiply a number by its multiplicative inverse or reciprocal, you're going to get 1. So when we multiply these two together, these two give us 1. And so we wind up with only 1k, or just k, since we don't usually write the coefficient 1. And then we have to multiply the other side of the equation by the -7/2 over here. And so we wind up with -70/2 or -35 as our final result. And remember, as in every other situation, you can take your answer and substitute back to check. It's not a requirement, but you know, it's a good thing to do for yourself to make sure you didn't go off the beaten track somewhere. So if we have -2/7 times -35, and the question is that equal to 10? Well, we have +70/7 is equal to 10, and of course this is 10. So 10 is equal to 10, and that is correct. Let's take a look at some problems involving solution of equations using multiplication and division. So, for example here, solve for x. 5x equals 3x minus 6. Now, if we want to isolate x, we're going to have to remove the 3x from the right side of the equation. We do that by subtracting 3x from both sides. This gives us 2x. These cancel. 2x equals -6. Now we can divide both sides by 2 using the multiplication rule of equality. And so therefore x is equal to -3. Let's take another look. Well, here we have 4y minus 14, write this a little larger to make it easier to work with. So we want to collect like terms. Subtracting y from both sides, we'll get 3y, and then adding 14 to both sides, we get 14 minus 2, which is 12. And so y is equal to 4. Now, we used division law here, dividing both sides by 3. And so this is an example of where we use not only our previous rules, but also now multiplication and division. If we want to know if we're right, we put the 4 back into the original equation. Does 4 times 4 minus 14 equal 4 minus 2? Well, this is 16 minus 14, that's 2, and 4 minus 2 is 2. And so we see that the answer is correct. And it's always reassuring to do the check, because even if you're not told to do it, it tells you that you didn't make any mistakes. And remember, if you're doing a check, you have to go back to the original. So when we're checking this answer, we have to go back to the original equation and make sure we don't put it in somewhere along the way. Let's take a look at solving equations that involve combining like terms. Now, what do we mean by like terms? Like terms are terms that contain the same variables, and those variables are raised to the same corresponding powers. For example, if you have 5a squared b and you have 7a squared b, these are like terms because both of them involve the same variables raised to the same powers. Doesn't matter that the coefficients are different numbers. The like terms are determined by the variables, and that the variables are the same and they're raised to the same power. Now, if you took an expression like 2ab squared, for example, even though both of them involve the letters a and b, they do not involve the same powers of a and b. So this would not be a like term for the ones that you see above. Okay. Now, to solve this equation, before we do anything else, we have to distribute the 3. So notice the 3 is distributed over the x minus 2 to give us 3x minus 6. Once we've distributed those, remember, we're the order of operations, we're doing the multiplications before we do additions and subtractions. Now we can combine like terms. We can use the subtraction property of equality to subtract the 3x from both sides and add the x to both sides. And so this gives us minus 2x minus 3x plus x. And then we can subtract 6 from both sides. So we have minus 6 minus 6. And this gives us negative 4x is negative 12. Divide both sides by the negative 4, and x comes out to be a positive 3. Okay, looking at combining like terms in additional equations. Here we see in the left side of the equation, we have the like terms 5x and 6x. So those can combine to give 11x. We also have like terms 5 and 12. So those can combine to give 17. Now, if we wish to have all of the terms with variables on the left side, we can subtract 7x from both sides, giving us 11x minus 7x, or 4x. We can subtract 17 from both sides, giving us 4. And so dividing both sides by 4, x is equal to 1. Right, this goes through what we just talked about. Using the commutative property, they brought all the things over. They did it a little, they showed a little more detail than I did when I did it. And then subtracting 7x from both sides, subtracting 17 from both sides, dividing both sides by 4. There's a lot you will find after a while, after you have a certain amount of experience, that you do certain things mentally. So for example, you recognize that you can bring the 7x over, combine the like terms. You do a lot of this as a kind of mental process. But in the beginning, you may want to write out, even though you think they're kind of baby steps, you may want to write them out to make sure that you don't make any errors. And of course, when you're finished, you want to go back and make sure that your answer works. So if we subtract x equals 1, we have 5 plus 6 plus 12. Does that equal 7 plus 21? And here we have 10, 16, and 12 is 28. And 7, I'm sorry, it's times, it looked like a plus, 28. So 28 equals 28, and the answer checks. Okay, again, looking at equations by combining like terms. In this case, we would combine the 39 with the negative 15 to get plus 24. And we have 3m plus 24 is equal to 3m minus 15. And you might already be able to see that that's ridiculous, because if you have 3 times some number m and you add 24 to it, it can't possibly be the same as 3 times m with 15 subtracted from it. So in and of itself, this seems to show you that this doesn't make any sense, and therefore there isn't going to be an answer. However, if we carry it through just using the normal processes, we would subtract 24 from each side and then subtract 3m. So we have 0 equals minus 15 minus 24, which is negative 39. And of course, 0 is not equal to negative 39. And so we see that this is a ridiculous answer. And the conclusion is that the answer is the empty set. Okay, there is no solution. Okay, they did the process in a little bit differently than I did. In this particular case, they started by subtracting 3m from both sides and didn't bother with the whole, with these. They just combined the like terms here, combined the like terms there, and wound up with 24 equals negative 15, which is equally silly, obviously not true, and so there's no solution. And remember that we show an empty set this way, well, without the little flag at the top. Sorry. See if I can erase the little flag. Empty set that way or this way. Okay, so this shows set notation with nothing in it, therefore it's empty. You don't put anything in there, not even this symbol, because then it wouldn't be empty, or you just use this symbol, the phi, from the Greek alphabet. Okay, let's look at another equation that involves combining like terms. Okay, here we have 5 minus y plus 4y minus 4 minus y plus 2 equals 15. All right, so we can use the commutative property of addition to move the whole numbers around and to move the terms involving the variables around. So we get 5 here minus the 4 there plus the 2 there. So this gives us 5 minus 4, which is 1 plus 2 is 3. Oops. For some reason, this doesn't want to work very well. Let's see if we can. Maybe this will work now. Okay. A little bit of computer acting a little bit temperamental there. Okay, so we have 5 minus 4 is 1, 1 plus 2 is 3. Negative y plus 4y minus y gives us plus 2y, and on this side we just had the 15. So subtracting 3 from both sides gives us 2y equals 12. Divide both sides by 2, and we wind up with y is equal to 6. If we want to check, we have to go back and put the answer into the original equation. So this would give us 5 minus 6 plus 4 times 6 minus 4 minus 6 plus 2 equals 15. And remember your order of operations, so you have to do the 4 times 6 first, because that's the multiplication. That gives you 24, and then you just add from right to left. And you wind up with the answer that one side 15 equals the other 15. Okay, now when equations contain parentheses, remember parentheses are used to show multiplication. And we have a distributive property of multiplication with respect to addition. So if we're going to use this property, we use it when we see that we have a multiplication with respect to an addition. And in solving the equation, we have to apply the distributive property first, because remember the multiplication is always going to take priority over the addition and subtraction. So here we have the -3 times the x minus 1, we distribute, -3x plus 3. Remember, -3 times a -1 would give us a positive result. 4x plus 4 is equal to 3x minus 6 plus 1. So now we've cleared out all the multiplications. Now we can combine like terms. So the -3x and the positive 4x will give us x. The 3 and the 4 will give us a 7. And then the -6 and the positive 1 will give us something which doesn't look correct here. Let's see. I guess they didn't combine them. Okay. Didn't combine all the like terms. So this would be actually x plus 7 equals 3x. And if we want to combine the like terms, we would make this a -5. Okay. So then x plus 7 minus 3x. I'm sorry, this solution is just a little bit bizarre. Not really the way I would normally do it. Let's see what the next screen looks like. Maybe I have a, right, that's a different screen. So let's go, and I'm just going to do this the way I would prefer to see you do it without so much complication. So let's just go from the x plus 7 is equal to 3x minus 5. Then you can subtract 3x from both sides and subtract 7 from both sides, and then divide both sides by -2. So it's fewer steps, and I think you can see it more clearly. I hope that's the case, that you can see this more clearly, because I think it's a little better. Sometimes we can be so specific about every little, I don't know, little bump in the road that it becomes more complicated. But I think this is definitely the easiest way to do it. So you have to first use your distributive property. That's essential. And you do have to combine your like terms, but they didn't combine all the like terms here. So I would say combine all like terms as we did here, and then you can combine all the terms involving the variable and do your final division, which is a much simpler result. Of course, if you want to check, you do have to go back and check in the original equation. So we would have -3 times 6 minus 1 plus 4 times 6 plus 1 equals 3 times 6 minus 2 plus 1. And so this gives us -3 times 5 plus 4 times 7 equals 3 times 4 plus 1. So -15 plus 28 equals 12 plus 1. And this is 13, and this is 13. And so it checks. And remember, the check is not for my benefit. The check is for your benefit, so that you can see if you did the problem correctly. And if you didn't, then you can go back and redo it. Now, there's another caveat that I want to bring into this situation. When you go back to do a problem, don't look over the work you did before. Do it fresh, do it new on a separate sheet of paper or without seeing what you did before. My high school teacher used to say to me, when you look over your work, You overlook your errors. And I have remembered that all through my years of studying mathematics and teaching, because it's true. When you look over what you did before, you kind of fall into the same rut. You don't see any errors you might have made. You take a fresh sheet of paper, you don't look at what you did before, you start fresh, and then you compare your results. And that is the way you usually will pick up any errors that you make. Now let's look at another example involving the solution of an equation containing parentheses. Remember, first we have to do the multiplication, so we have to clear the parentheses. So we're going to have 4x plus 28, minus 36 equals 13x minus 26. Okay, there we have the result of the distribution. Now we have to combine like terms. The plus 28 and the minus 36 gives us the negative 8. So we now have 4x minus 8 equals 13x minus 26. The person who set up this slide decided to put the variable on the right-hand side. That works. You can do it that way too. And I suppose the thinking was that if we subtract the 4x from both sides, we're going to have a positive value of 9x here rather than dealing with negatives over on the left-hand side. So here we have negative 8 equals 9x minus 26, then adding 26 to both sides, we have 18 equals 9x. Subtracting both sides by 9, we get 2 equals x. Now remember that equality has something called a symmetric property. Symmetric property of equality says that if A is equal to B, then you can also say B is equal to A. Symmetry, they work the same both ways. So in this case, we got 2 equals x. There's nothing wrong with that, but people usually put the variable first. So if you want to, you use the symmetric property of equality and you say that x is equal to 2. Let's look at another example in solving an equation involving parentheses. Okay, solve for k. 3 times 3k minus 2 minus 6 times 4 minus k equals 24k minus 4 times 7k minus 2. Okay, what do we have to do first? If you said distribute, you would be correct. So 3 times 3k minus 2 gives us 9k minus 6. And now we distribute here, minus 24 plus 6k. And that equals 24k minus 28k. And remember, distribute the negative 4 plus 8. Okay, moving along. Right, here we have the distributive property as we worked it out on the previous page. Now we're going to combine like terms. We have to look for the like terms, the 9k and the 6k here. Okay, so we have 15k on the left-hand side. The negative 6 and the negative 24 gives us a negative 30. On the right-hand side, we have the terms in k, which come out to negative 4k, and the constant term. Now we wish to get all the variables on the left side and all the constant terms on the right side, so we're going to add 4k to both sides, giving us 19k minus 30 is equal to 8. Subtract, we have a negative 30, so we're going to add 30 to both sides. We have 19k is equal to 38. Divide both sides by 19, and k is equal to 2. Now, if you want to check, you go back, you put this into the original equation. So we wind up with 3 times k is 2, so this is 6 minus 2, whoops, which is 4. I guess I can't do it up there, causes too much problem. Let's see if I can do it down here. 3 times 6 minus 2, which is 4, minus 6 times 4 minus 2, which is 2, equals 24 times 2, which is 48, minus 4 times 14 minus 2, which is 12. So we have 12 minus 12, 0, 48 minus 48, 0, and so the equation checks. All right, let's look at another example of equations, solving equations which contain parentheses. Okay, let's take this question. 5 times x minus 3 minus 7 times 6 minus x plus 29 equals 50 minus 3 times 8 minus x. Okay, remember, again, a lot of parentheses containing terms, therefore we have to distribute. Okay, using the distributive property, 5 times x minus 3, we're going to have 5x. We do have an eraser here. 5x minus 15 minus 42 plus 7x plus 29 equals 50 minus, now we have the 3 times the 8 minus x has to distribute, so that's minus 24 plus 3x. So moving along, here's the result that we got from our distribution. Okay, we're going to combine the 5x and the 7x on this side of the equation to get 12x. Combine the constant terms to get minus 28. Combine the constant terms on the right side to get 26. And we have our variable here. We subtract the 3x from both sides. So we now have 9x minus 28 equals 26. Add 28 to both sides, which is 9x equals 54. And then dividing both sides by 9, we have x equals 6. Now, how do we check that that answer is correct? We go back to the original. So we have 5 times 6 minus 3, which is 3, minus 7, times 6 minus 6, which is 0. So this is just going to wipe out. Plus 29 is equal to 50 minus 3 times 8 minus 6. 8 minus 6 is 2, so that's minus 3. That's 50 minus 6. So we here have 15 plus 29, which is 44. And here we have 50 minus 6, which is 44. So we wind up with 44 equals 44, and the problem is checked. Now remember, there's nothing here that said you had to check it, but for your own benefit, so that you know you did it correctly, you're going to want to check it. And remember that in checking, we always go back to the original equation. Okay, now we want to look at graphing a solution set on a number line. We've worked with number lines before. You know that the real numbers are represented on the number line in order from least to greatest, and that we show points on the number line with numbers that are called the coordinates of those points. And the point has a coordinate that is a unique number that corresponds to it. So if a point has the coordinate 3, it can't have a different coordinate, you know, at a different time of day. If its coordinate is 3, its coordinate is 3. And that number is unique. So for instance, if you look at this number line here, the points that are indicated in red correspond to coordinates of -4 for A, -2 for B, 0 for C, and 3 for D. Now, if we wish to graph the solution set on a number line for an inequality, we can look at it when x is just an integer. So if we want just integers between -4 inclusive and 2 not being included, we would have -4, -3, -2, -1, 0, and 1. And those are shown right here on the number line as individual discrete points. But if x is a real number, we have to include everything between the -4 and the 1. So this then means that we shade everything between the 2 points. Now, since the -4 is included, this is made solid, but the 1 is not included, so we show this by means of an open circle at the 1. All right, so supposing we want to graph this set of numbers on a number line. Okay, looking at this set of numbers, -3, -1, 0, 1/2. Now, 1/2 is not specified in the scale that we've indicated, but we estimate it, and so we put its position on the number line in a way that we think makes it pretty clear that it's halfway between the 0 and the 1. We have 2, and then we have 4.5, again, estimating the position of the 1/2 between the 4 and the 5. Now, say we have the following inequality and we want to graph its solution set if x is an integer. So this means integers that are greater than -2, but less than or equal to 4. So if we look at our number line, if it has to be greater than -2, we know that we're not going to include the -2. But if it's less than or equal to 4, we know that the 4 is going to be solid. If x is an integer, we're going to include all of the integers between these. If it's a real number, then we would shade in the entire thing. But in this case, we have just an integer, so we have -2 not included, okay? It's an integer, so it's not shown. We have the -1, 0, 1, 2, 3, and 4. 4 is included, so we see it on our answer. Wish to name the numbers that are represented by the graph shown. Since we see these are discrete values, okay, between -2 and -3, we would have to estimate. It looks like it's halfway from the way the hatch marks are made. So -2.5 would seem to be in the set. Also -1, 0, 1, and then 1.5. Now you can denote this as -2.5 also if you wish. You could denote this one as 1.5 if you wish. All of those are correct and equivalent. You could even denote this as -5/2 and denote this as 3/2. They're all mathematically equivalent. So usually if you pick one, you're sort of consistent with it. If I'm going to do it as decimals, then I probably would do the other side as decimals. If I'm going to work with mixed numbers, I probably keep the other end as mixed numbers. And again, with fractions, keep it as simple fractions or common fractions. All right, in this case, the answers were listed as mixed numbers. Okay, let's look at some problems which involve solving equations and what we would call applications of solving equations. In other words, we have a problem situation, we set up an equation. The idea is to describe the problem situation by means of the equation. So, supposing we know we have 40 students in a class and the number of boys is 7 more than twice the number of girls, and we want to find both. Now, my inclination would have been to approach this a little bit differently. So let me show you what I would be more inclined to do first, just because I think it's a little easier, but I'll show you both of them. My inclination is, since boys are described in a more complicated way than the girls, I would be inclined to let X be the total number of girls. And then the boys would be 7 more than twice the girls. So that would be 7 added to twice X. And that would be the number of boys. And then the total is 40. So I would then say X plus 7 plus 2X equals 40. I guess if I don't get this thing off the pad fast enough, I get strange ghost lines. Okay, so we have 3x equals 33, and so x equals 11. And that, remember, is the number of girls. And then the boys are 7 added to twice the number of girls, so that would be 22. So 29 would be the number of boys. So this, I think, is a little bit easier. But another way of doing it is that you could let X represent the number of boys. Okay, let the total, 40 minus X, represent the number of girls. And then you form an equation between the two. Okay, the boys are equals 7 more, 7 added to, twice the number of girls. Then you solve this equation by distribution, combining like terms, and you wind up now, instead of X originally being the number of girls, you wind up originally with X being the number of boys. And then, of course, you take 40, subtract the number of boys to get the number of girls. Now, some people will see this way as the simplest way, you know, and they'll love that. Okay. And others will see this as a simpler way, and they'll love that one. Well, it doesn't matter. You can see they both wind up the same way. But what is the key? The key is setting up your variables so that it's very clear what everything stands for. If you make that very clear, then you can translate from your variables into the sentence that describes their relationship. And then, of course, since everything has been expressed with great clarity, at the end, you know what the X stands for, you know what everything in each expression stands for, and you can see that either way will lead to the correct solution. And with most problems, there's not just one way of approaching the problem. Okay, let's look at another problem, which perhaps is a little bit simpler, actually. 3 times a given number decreased by 10 equals the number. Find the number. So if supposing we let the number be n, 3 times the number is 3n. Decreased by 10 means we take 10 away, and that equals a given number. This is a much simpler problem. Okay, subtracting n from both sides, adding 10 to both sides, the number is equal to 5. Let's see if that works. 3 times 5 is 15. If we decrease it by 10, do we get the given number of 5? Yes, we do. Yes, I guess that there was no official solution here, so I'm glad that I showed you one. Okay. Solving equations in another application. In an election, 2 opposing candidates received a total of 2,638 votes. One candidate received 124 votes more than the other. How many votes did each candidate receive? Well, again, I don't know if we have a solution listed here. Yes, we do. Okay. So if we let V be the number of votes that the first candidate receives, and then V plus 24, since one received 124 more than the other, is the number received by the other candidate, together they make up the total number of votes. We then have to combine like terms. 2V plus 124 is 2,638. Subtracting 124 from both sides, we get the value of 2V. Subtracting both, dividing both sides by 2, we get the value of V. Now remember, V stood for candidate 1. So candidate 1 receives 1,257 votes. Candidate 2 gets 124 more. So candidate 2 gets 1,381 votes. And when you take these totals, they should add up to the 2,638, which they do. Okay, let's look at another example which involves solving equations. A man has $65 in $10 bills and $1 bills. He has 3 times as many dollar bills as $10 bills. How much of each kind does he have? Now remember, we was talking earlier about problems in which you had to distinguish between number and value. Whenever you have problems involving money, the number of a certain number of coins or the number of a certain number of bills versus the value of those bills. So here we can talk about how many $10 bills, how many $1 bills, that's number. But if we're talking about the value, then of course the number of $10 bills has a value that's 10 times as great. In terms, if the number is say n, then the $10 bill's value would be 10n, whereas the $1 bill's value would only be 1n. So we need to find a way of distinguishing in our solution both the number and the value of the bills. And you have to have this very clearly in your mind. So supposing we let B stand for the number of $10 bills, sort of a good choice, B for bills, okay? 3B then would be the number of $1 bills, because we're told he has 3 times as many $1 bills as $10 bills. Now, what's the value of this money? Well, the value of B $10 bills is 10 B dollars. And the value of 3B $1 bills is 3B times 1. So total value is 10B plus 3B, and that makes up our complete value for all the money put together. This then gives us a total of 65. 13B is equal to 65. And I would be inclined, if you do these problems, do not carry dollar signs over. I know that it was probably put in here to remind you about the difference between number and value. But if you make a very clear table here describing what everything stands for, I would leave this out, only because there's a tremendous temptation, since this is a symbol, to kind of get it confused with the algebraic symbols in the problem. So I would tend to just leave these out and make it 10B plus 3B is 65, 13B is 65, then divide both sides by 13, and you get B is 5. We know B stands for the number of bills, so the man has 5 $10 bills and 3 times as many 15 $1 bills. Now, when we want to solve for a specific variable in a formula, this involves being pretty careful. For example, if we have the circumference of a circle and we want to know what is its radius, we know a formula that relates the circumference to the radius. That formula is C equals 2 pi r. Okay, and I would be very careful if you're writing formulas not to use x for multiplication. I would say if you want to use any symbol at all, use a dot, because it's too easy to misrepresent the x as a variable. So we know C is 2 times pi times r, where C is the circumference, r is the radius. We want to isolate r in the formula and then substitute the values for C. So to isolate r, we would have to divide 2 pi by both sides, and we wind up that r is C divided by 2 pi. Now, you could also do this by substituting in your numbers and then finally solving for r in the end. If you find the work with the algebra too complicated, that is a possibility. Okay, so we wind up with r is C over 2 pi. Now, you can, in many instances, express an answer and leave pi in the answer. That would give you what we would call an exact answer. However, if you need an approximate answer, then you have to use an approximate value for pi. Typically, we would use 22/7. Some of you may have also seen pi used as 3.14. In these examples, we're using 22/7 as an approximate value for pi. Remember, pi is what we call an irrational number. And if you remember from your first lesson, irrational numbers are numbers that go on forever. They never come to an end. They don't have a standard pattern that repeats itself. Pi is an example of such a number. So if we want to figure out about how much something is, and pi is in the answer, we have to use an approximation. And we have to figure out how many places should we take pi to in order to make the answer reasonable. For most of the stuff that we do in the algebra course, it's good enough to use something like 22/7 because we're not interested in the arithmetic so much as we are in the process. Okay, so complete the chart. We would have that in the first case, case A, if the circumference is 440, then the radius is going to be 440 divided by 2 times pi. And remember, if we're dividing by 2 times 22/7, the 7 is going to flip up into the numerator. And the same thing holds in the remainder of these problems, the same process for calculation. The formula for the area of a trapezoid is 1/2 h times b1 plus b2. Remember that a trapezoid is a quadrilateral, that is a 4-sided figure, and it has a pair of parallel sides. Those are called the bases. Okay. And the altitude or height of the trapezoid is the vertical distance or the perpendicular distance between the bases. So that the height here is denoted by the h, sometimes called the altitude of the trapezoid. Okay, and the bases are b sub 1 and b sub 2, 2 different bases for the trapezoid. If we want to calculate an area, okay, and we want to find B, for example, in terms of AH and B sub 1 in terms of AH and B sub 2, we can isolate B sub 1, little bit of a complicated problem. Okay, so first we would want to get rid of the 1/2 so we can multiply both sides of the equation by 2. This then gives us 2a equals h times b sub 1 plus b sub 2. Notice how much easier it is already because we got rid of the fraction. All right, now if we want to isolate one of the bases, which is the b sub 1, we're going to divide both sides by h to get the h out of the situation right here. Okay, so 2a over h gives us b sub 1 plus b sub 2, and now it's quite simple to get b sub 1 by itself. You just subtract the b sub 2. Another issue where we could be solving for a specific variable, you may remember from your geometry studies, the formula for an angle that's formed by two secants. Now, I don't know if you remember what a secant is. A secant in a circle is a line that intersects the circle in two distinct points. So AB and AC in this diagram are secants. Okay, and they intersect, A intersects at D and B, and A intersects, the other secant intersects at E and C. The angle that these two secants form with each other, this angle right in here, okay, is measured as 1/2 the difference between the two intercepted arcs. So this is one intercepted arc, arc BC, this is the other one, DE. So the measure of angle A is 1/2 the difference between the measure of arc BC and the measure of arc DE. And say we want to find the measure of arc BC expressed in terms of the other variables in this formula. Okay. So what we would have to do first is get rid of the 1/2, so we multiply both sides by 2. This gives us 2 times the measure of angle A is 2 times this, and then of course what's going to happen is that these will cancel. So 2 times the measure of angle A is the measure of arc BC minus the measure of arc DE. Since we're looking for the measure of arc BC, we can subtract the measure of arc DE from both sides, and we wind up with the measure of arc BC is equal to twice the measure of angle A plus the measure of arc DE. And of course, you can use the symmetric property of equality if you want to write this first. All right, we have the circumference of the circle, standard formula, 2 pi r, but we want to solve for r in terms of c and pi. What that means is we want to isolate r. So the question is, how do we isolate r if these are multiplying r? Well, to undo the multiplications, we have to do division. So we can divide both sides by 2 pi. The 2 pi's will divide out of numerator and denominator, and we will then have r expressed in terms of c and pi. R is equal to c divided by 2 pi. Now, up to now, we've focused our attention entirely on equalities or equations. We also want to look at when things are not equal. And of course, more often than not, when we're dealing with mathematics, things don't come out to be the same. They come out where one thing is bigger than something else, or bigger than, or possibly equal to it. These are the symbols that are used in expressions of inequality. This symbol means less than. This symbol, this is less than. This is greater than. And if we put a bar under it, it means or equal to. So here we would have less than or equal to, and here greater than or equal to. And of course, the equal sign with a slash through it means not equal to. So we have, just as we did for equalities, we have rules that apply to inequalities. One of the things that's very important about inequalities, at least where real numbers are concerned, is that you can put the numbers in size place. And so you can always tell if one is greater than or less than the other or equal. This is called trichotomy, tri from 3, because there are 3 possibilities. If you have 2 numbers, A and B, then either A is going to be less than B, or A is going to be equal to B, or A will be greater than B. It seems kind of obvious, but it's quite important, and you'll see that it is quite important to have this clearly in mind when you're dealing with numbers that are not equal to each other. What is their relationship? Which, if any, is greater? Which, if any, is less? Or are they possibly equal? We have, just as we had for equality, we have a transitive property of inequality. Remember, trans goes across. Transit systems, you travel on transit systems to go across, say, from one part of town to another. Okay, so this sort of suggests the meaning for a transitive property. If you have A is less than B, and you also have B is less than C, then this implies, this is and B is less than C, it implies that A must be less than C. Again, it's sort of obvious, okay? If, say, Alfred is younger than Bob, and Bob is younger than Carol, okay, then Alfred must be younger than Carol. And the same thing will work for greater than. If X is greater than Y, and Y is greater than Z, then it must follow that X is greater than Z. Sorry about these stray marks. This thing is terribly sensitive. Okay, X greater than Y, Y greater than Z, so X greater than Z. So these are transitive, goes across like traveling across. Addition and subtraction properties for inequalities. If A is less than B and you add the same thing to both, you keep the inequality. We preserve the order of, what we say, we preserve the order of the inequality. If A is greater than B, then adding the same thing to both sides, again, preserves the order of the inequality. So the result from the first one, where the first term was less than the second, then when we add the same thing, we still have that relationship that the first is less than the second. And if it starts out with the first is greater than the second, and we add the same amount to both, we still have that same relationship. If A is less than B, and we subtract the same amount from both, we keep the order of the inequality. A minus C is less than B minus C. If A is greater than B and we subtract the same amount from both sides, again, we keep the order of the inequality, right? So let's see how these work out, how these laws work out in terms of solving an inequality expression. Let's consider this expression: 5 plus m is greater than or equal to -2. Okay, that's our given inequality. If we subtract 5 from both sides, we wind up with just m on this side. The plus 5 and the minus 5 cancel out, okay, or add to 0 is the more mathematical way of saying it. And then the -2 and the -5 add to the -7. So m must be greater than or equal to -7. If it's a real number solution, which is what we've really specified by, if we don't specify something else, we mean real number solutions, we see m has to be greater than or equal to -7. So we start at -7, and then we move to the right until we go on, well, we go on forever. So we move to the right. It's an infinitely long solution set, all numbers greater than or equal to -7. Okay, supposing we want to solve the following inequality for the unknown graph the solution set. To isolate the z, we have to add 6 to both sides. Adding 6 to both sides, we would have z is less than, because remember, we're adding the same thing to both sides of the inequality, so we're not changing the order of the inequality. So we have z is less than 4. To graph z is less than 4, we have to show the arrow going to the left, but since it's less than but not equal to, remember, we show that as an open circle. A little bit more complicated inequality. Here we would have to subtract 2x from both sides. Subtracting 2x from both sides, we're going to have x plus 7 greater than or equal to 10. Now we can subtract 7 from both sides, so x is greater than or equal to 3. When we graph this on the number line, we see since it's greater than or equal to, the 3 is included, and it's greater than, so it moves to the right. Same idea, solve the inequality and graph the solution set on a number line. Notice like terms here. So we're going to just have y plus 2 not equal to 5. Subtracting 2 from both sides, y not equal to 3. And so that would be everything on the number line except for 3. So you show that by the arrow going in both directions and just leave a hole at the number 3. Now, when things get a little more interesting, solving inequalities using multiplication and division, as well as using addition and subtraction. Let's take a look at the following problems, because when we have multipliers, then depending on what multiplies the inequality, it may change the order of the inequality. Okay, if we have a and b as any real numbers and c is a positive number, then the order of the inequality is preserved. Okay, so we multiply an inequality by a positive number, we keep the inequality as it started out. So if a starts out less than b and we multiply by positive c, then ac is less than bc. If it's the other way around, if a is greater than b, we multiply by a positive number, we preserve the original order. But notice that when c is negative, it reverses the order of the inequality. And this is very important, reverses the order. So if a is less than b and we multiply by a negative number, ac will be greater than bc. If a is greater than b and we multiply by a negative number, then ac is less than bc. The easiest way to see this is to just take some examples. Okay, if for example you take something, the negative one is the hardest to see, so let's think about that. Supposing you have 3 is less than 5, and say you multiply by negative 2. So you have negative 6 and negative 10. Well, negative 6 is a greater number than negative 10. So you can see that the order is reversed. Okay, same thing happens for division. Works the same way as the multiplication. If you divide by a positive number, you preserve the inequality. If you divide by a negative number, you reverse the order of the inequality. So for example, supposing you're told to solve an inequality, negative 5y is less than 25. To get rid of the negative 5, you're going to divide both sides of the equation by negative 5. When you divide by negative 5, it reverses the order of inequality. Notice that the negative the less than changes to greater than. Okay, when you divide both sides by the negative 5. So the solution winds up being that y is greater than negative 5, which shows us as negative 5 not included, and then going to the right. So let's take a look at a few examples that involve solving inequalities using multiplication and division. All right, this one pretty straightforward because we're going to divide both sides of the inequality by a positive number. Therefore, it's going to keep the order of the inequality. The 4's will cancel, divide out. We have y greater than or equal to negative 5. If it's greater than or equal to negative 5, remember the negative 5 is included. Greater than means we move to the right. And here we have a nicer version of the solution, showing the solution from negative 5 moving on to the right. And the process dividing both sides by the positive 4 does not alter the nature of the inequality. Okay, taking a look at the next question, solve the inequality, graph the solution on a number line. Okay, think for a moment about what you would want to do. I hope you're thinking that the best thing to do first is to isolate the term containing x. So to do that, we would have to subtract 3 from both sides of the inequality. And we would then have 2x, these would add to 0, and we'd have 2x is less than 8. Now we can divide both sides of the inequality by a positive number 2. Therefore, the inequality is not going to change its order, and we will have x is less than 4. Take a look at this. X is less than 4. To show on the number line, we have 4 not included. Less than means this moves to the left. Okay, another question involving inequalities. Solve the inequality, graph the solution on the number line. Now, I think you might already have the alarm bells ringing because you see that minus 4a. But it's good if that sets off the alarm, because that will remind you that when you're going to divide at some point by a negative, you're going to have to reverse the order of the inequality. But before we do that, let's isolate the term that contains the variable. So to do that, we're going to subtract 5 from both sides of the inequality. This adds to 0, and we have minus 4a is less than 12. Now, to get the a by itself, we're going to divide both sides by minus 4. When we do that, when we divide by the minus 4, this is going to reverse the inequality. So this is now the correct statement. Minus 4a divided by minus 4 is going to be greater than the 12 divided by minus 4. So this adds to positive 1, and we get a is greater than negative 3. Okay, you see solution here. And I would personally, at this step, I would prefer to make this greater than. Because once you've divided by the negative 4, the sign of the inequality has changed. Now, it's not terrible, it's not really a mistake if you don't do that, because as long as you ultimately change it to the greater sign, you're fine. It's just that I think you want to sort of signal as soon as you can to yourself that the sign of that inequality has altered once you perform, or even show that you are going to perform this division. All right, so a greater than negative 3 shows a as a number moving to the right on the number line, and negative 3 is not included. Okay, so let's see how these inequalities can show up in a problem situation. Supposing we take this problem. Fred is trying to earn at least $300 before Christmas by selling boxes of candy at $3.50 a box. How many boxes must he sell to reach his goal? Well, first we do want to define our variables. So supposing B, which is a good choice, it sort of reminds you that stands for the number of boxes Fred needs to sell before Christmas. We know that each box is going to cost $3.50. We don't include the dollar sign. We know it's in dollars, okay? So $3.50 times the number of boxes is going to give us the total revenue. He has to have more than $300, or he could have $300. When we say at least 300, it means it could be 300 or more, okay? So therefore, to show 300 or more, we have greater than or equal to 300. Now, dividing both sides of this equation by 3.5, we get that B has to be greater than or equal to 85.714. Now, of course, when you're dealing with the boxes of candy, you're not going to deal with fractional boxes. You have to have whole numbers of boxes of candy. If he sold 85, that would not give him enough revenue. So he has to go up to the next whole number. He has to sell at least 86 boxes in order to earn at least the $300 before Christmas. And we see that checking the result, that 86 times the 3.5 gives us a number, 301, which is greater than the $300. If we were to go drop down to the 85, you would perform the multiplication, you would see that you do not get revenue that is greater than or equal to the $300, and so you have to go up to the next whole number of boxes. So many of these things you will see just involve thinking about it in common sense terms. Once you get an answer, it's like, does this answer make sense? Let me see if it works out. You know, you can always be challenging yourself to see if what you're getting is reasonable. Okay, let's take a look at the next problem. It says the sum of two integers is at most 30. One integer is 7 more than twice the other. Find the greatest integers that will satisfy these conditions. Well, what does it mean when we say that that the sum is at most 30? Well, in order for it to be at most 30, it means it cannot be more than 30. So that means it has to be less than or equal to 30. So if we set up variables, let's let x be the first integer, 2x plus 7 be the second integer, we know that the sum of the two has to be less than or equal to 30. That means the most it can be is 30. Okay, so 30 is the top. That would be equality, or it can be less. That would satisfy the meaning of the at most. Remember, you're constantly trying to interpret or translate from an English sentence to an algebra sentence, in effect. Okay, so now we have 3x is less than or equal to 23 by subtracting 7 from both sides and combining our like terms. And so x must be less than or equal to 23 thirds or 7 2/3. So the greatest integers, because remember it said integers, did not allow us to use fractions. The greatest integers then must be 7 and 21. Let's look at another problem which involves using inequalities. Whenever you see something maximum or minimum, you know you're dealing with something that has some upper or lower limits, and we are dealing with an inequality problem. This question says the perimeter of a rectangle is less than 100. If the length is 15 feet more than the width, what are the maximum dimensions of the rectangle? Well, if we set up a diagram, okay, we have the width is W, which is suggestive of width, and length is 15 more than the width. So it's a good idea. Call that W plus 15. Okay. We know the perimeter of the rectangle involves 2 of these W's and 2 of the lengths, W plus 15. Okay, so to get the perimeter expression, we have to add all of these together. In other words, 2 of the W's, 2 widths, and 2 of the lengths, and that has to be less than 100. Adding these up, we find 2W plus 2W plus 30 are less than 100, so 4W must be less than 70. W must be less than 17 and a half. Okay. We're making an assumption here, which I don't believe was stated in the problem, that you cannot have a fractional width or length, that you have to have a whole number answer, and therefore the maximum dimensions are 17 by 32. You have to be careful with these problems sometimes to make sure that the conditions are set out very clearly. This is a little bit vague, but generally speaking, in a simple problem, you're going to want the dimensions to be whole numbers. They should, however, have said whole numbers just to make sure that you wouldn't include the possibility of fractional answers. Okay, here's one that you might be able to relate to, given that everybody is on his or her cell phone these days. Supposing we have a basic charge per month for cell phone A is $30, and then the overtime charge is 7 cents a minute. On a different cell phone system, cell phone B, there's a basic charge of $35 a month, but an overtime charge of only $4 per minute. When will cell phone B be a better deal than cell phone A? In other words, when will cell phone B be cheaper than cell phone A? Well, if we set up the amount that each costs, cell phone A's cost per month is going to be our basic charge of $30, and then the overtime charge is 7 cents per minute. So we have to specify something to stand for the overtime minutes. Logical, M would be a good choice for the overtime minutes. Okay, so M for minutes. So the cell phone A cost is $30 plus 0.07. Remember, cents has to be represented as $0.07 here because we're working in dollars throughout, times the number of minutes. Cell phone B then, a basic charge of $35, but 4 cents a minute. Question is, when will A cost more than B? So when will 30 plus 0.07 M be greater than 35 plus 0.04 M? Well, this will come out when M is greater than 166 and basically 2/3 minutes. So when you speak more than 167 minutes, because these things are always done in whole minute units, remember. When you speak more than 167 minutes, B will be the cheaper plan to follow. So there's a problem that you might really be able to relate to in a real life situation when you make a decision about which cell phone company you're going to work with. Another kind of inequality problem that we want to look at is something which is known as compound inequalities. Compound inequality is a statement involving inequality, either greater than or less than, but combined, inequalities being combined with the terms or and. Okay, and these have very special meanings in the world of inequalities. Okay, an or statement is called a disjunction. Okay, disjunction separating a distance or a separation between the terms. An and statement refers to something called a conjunction, which pushes them together. So a disjunction is a compound inequality where the inequalities are connected by the word or, and you use the symbol shown here for a disjunction. So for example, we have x less than or equal to -2 or x greater than 6. Okay, what would that look like? Well, if x is greater than or equal to -2, I'm sorry, x is less than or equal to -2, we would have -2 on the number line, and x would include the number -2, and then it would move off to the left. If x were greater than 6, we'd have an open circle at 6, then it would move off to the right. So this graph would show the disjunction that's described in this statement. Now, notice disjunction is a separation, and you see that the sets that describe the inequalities are truly separated. Now, when you get a conjunction is a compound inequality where the inequalities are connected by the word and we use the symbol, which is like the upside down V. So this would be read as x is less than 8 and x is less than or equal to 6. Okay, if we have x is less than 8 on the number line, that would be all the points going to the left of 8, but not including the 8. X less than or equal to 6 would involve all the points that are including 6 and then going to the left. Now, where does the overlap between these two sets occur? Only for x less than 6. This whole section in here does not satisfy both conditions. And if it's an and statement, it has to satisfy both conditions. So the final result would only be that the x is less than or equal to the 6. Okay, let's look at another example of a compound inequality using these ideas. Supposing we want to graph x is less than -1 or x is greater than or equal to 3. X is less than -1 means all the points to the left of -1, but not including the -1, which you see is an open circle. X greater than or equal to 3 goes to the right of 3 and includes the 3 as a closed circle. So this is a disjunction. Okay, the sets are separate, but both of them are part of the solution set if we were to write it in set notation. Okay, x less than -1 or x greater than or equal to 3 is the set notation for this graph, and this graph is the graph of that. Okay, so it works both ways. Now, the compound inequality, 3x plus 4 greater than or equal to 13 and x minus 2 less than 3. We want to take a look at each of these inequalities. So solving this one, okay, we get 3x plus 4 greater than or equal to 13, subtracting the 4 from both sides, 3x greater than or equal to 9. And so x must be greater than or equal to 3. Now, if we graph x greater than or equal to 3, we have this graph right here. If we have x minus 2 is less than 3, adding 2 to both sides, we have x is less than 5. Okay, we don't include the 5. We have everything shown in the blue. Now, if it is a conjunction, it means that both of these have to be true at the same time. This is true, and also this is true. So the only parts that satisfy the conjunction are the places where these two graphs overlap. So the solution set is what's shown here in the black. The parts where the blue graph and the red graph overlap each other. So the solution set would consist of 3 less than or equal to x, which is less than 5. And that would be the solution set of the compound inequality. Okay, so using some examples of disjunctions now. Remember, disjunctions are the inequality statements which involve or statements, okay? We have x is less than -1 or 2x is greater than or equal to 6. Okay. We would want to simplify this. If 2x is greater than or equal to 6, it means that x is greater than or equal to 3. So we're really dealing with a situation where x is less than -1 or x is greater than or equal to 3. Okay, x is less than -1 or x is greater than or equal to 3. So we have two disjoint sets. X less than -1 is shown by this part of the graph, -1 not included, and x greater than or equal to 3 shown by this part of the graph with the 3 included. Notice the sets do not overlap. They are disjoint. They're separated. Okay. Another example of a disjunction, 3x greater than 9 or -x is greater than 2. Well, if 3x is greater than 9, dividing both sides by 3, x must be greater than 3. But if we have -x is greater than 2, we would divide by -1. We would have x is less than -2. So our solutions, x greater than 3 or x less than -2, remember these 2 points are not included. The two rays make up the solution, and again we have disjoint sets. They do not overlap, but both of them are part of the solution set. Both rays make up the solution set. All right, let's look at another disjunction. 5x greater than or equal to -10 or 12 greater than 3x. We can solve again separately. If 5x is greater than or equal to -10, divide both sides by 5, x is greater than or equal to -2. Let's get rid of these stray lines here, perhaps. Okay, here we have 12 greater than 3x. Might want to rewrite this as 3x is less than 12, x is less than 4. So we have the disjunction, x is greater than or equal to -2 or x is less than 4. Okay, x greater than or equal to -2 or 4 is greater than x or x is less than 4. Okay. Now, because we're including everything that's in both sets, we see that the two blue rays, which show the individual parts of the solution, form the entire number line. So all real numbers satisfy that they are either in this set or in this set. But moving along to conjunctions, we want to solve the conjunction, x is greater than or equal to -2 and x is less than 3. If x is greater than or equal to -2, it's going to include the -2 and it's going to move to the right. If x is less than 3, it's not going to include the 3, but it's going to move to the left. So actually only the part where they two overlap, because this would go on forever this way and this would go on forever that way. But if it's the intersection, if it's the conjunction, it's the intersection, then it can only be the parts where they overlap. And so we see here is the x less than 3. I'm sorry, this is the x less than 3 over here. This is the x greater than or equal to -2 in the red. And so the solution is shown at the top in the black, the overlap of the red and the blue rays. All right, let's look at another example of a conjunction. Solve the inequality and graph the solution on a number line. Okay, conjunction of these two, we have 4x minus 3 greater than or equal to 1. So we're going to add 3 to both sides. So 4x is greater than or equal to 4, and therefore x is greater than or equal to 1. This part we have minus 2x is greater than 6 minus 4, which is 2. Dividing both sides by negative 2, we're going to have x is less than negative 1. If I can get rid of that straight line there. Well, I guess I don't want it to look like a negative x, but it's really hard to keep this from making straight lines. Okay, I think we've got it there. So we have x is greater than or equal to 1, and x is less than negative 1. Now, this should be setting off some kind of alarm bells for you, I hope. Because notice, if x is greater than or equal to 1, it looks like this. If x is less than negative 1, it looks like that. But we're looking for a conjunction. We're looking for values of x which satisfy both conditions. Well, notice there's no overlap. There are no x values which are in both sets. Okay, therefore, there is no solution to this inequality, this compound inequality, and we would show the solution as empty. Now you can graph the individual pieces, and that really helps to illustrate the idea of the empty solution, but you cannot find a solution set that satisfies the conjunction, the fact that they both have to be true at the same time. All right, another example, conjunctions. Solve the following inequality and graph the solution set. Okay. Negative 8 less than or equal to 3x plus 7, which is less than 1. Now remember, this really consists of two separate inequalities. Now you can separate them as negative 8 less than or equal to 3x plus 7. Let me go back, perhaps, do it this way. Negative 8 less than or equal to 3x plus 7 and 3x plus 7 less than 1. And then you could solve each one individually. Okay. Or, since it is a conjunction, you can just work across the conjunction. You have to be very careful, though. If you get in the habit of doing this, don't try to do it for disjunction, because remember, disjoint sets are separated. Okay, for this one, we can subtract 7 across the board, and this gives us negative 15 is less than 3x, which is less than negative 6. Dividing all through by 3, we get negative 5 is less than or equal to x, which is less than negative 2. And so this gives us the final result. I thought I had another example of a conjunction here, but it appears that we do not have another example of a conjunction written here. I guess I must have gotten a little ahead of myself. So let's take a look at just how you could do this as two separate expressions. Okay. So we can treat this as two separate inequalities, negative 8 less than or equal to 3x plus 7 and 3x plus 7 less than 1. Okay, so then we can add 7 to both sides. So we can divide this into a conjunction of negative 8 is less than or equal to 3x plus 7. Sorry, you wrote it wrong. And 3x plus 7 is less than 1. So subtracting 7 from both sides, we would have negative 15 is less than or equal to 3x, and therefore negative 5 is less than or equal to x. And we would have 3x less than 1 minus 7, so negative 6, and x is less than negative 2. So again, we would get exactly the same conjunction we had before, negative 5 less than or equal to x, which is less than negative 2. So we can treat them as two separate things, or we can sort of smush them all together into one, which is the way I did it in the first place. As long as you don't go around to smushing the disjunctions into one, you'll be fine doing it with the conjunctions. But always keep in mind that a disjunction is separate and not together. The conjunction is together. Just want to remind you as we end that your help sessions are this Thursday and Friday, and we're available to answer your questions at that time.